Well, in the last video, you learned about the two simplest kinds of reaction types: a synthesis reaction, where one product is formed from two or more reactants, and a decomposition, in which one reactant decomposes into two or more products. Today, we're going to explore three more reaction types and complete our set: single replacement, double replacement, and combustion reactions. In a single replacement reaction, one element replaces another one that's in a compound. The generic equation for a reaction like this, a sort of a general way of describing it, would be A plus Bx for our reactants, where A is an element that's by itself and B is an element that's part of a compound that will replace A. Maybe they're similar, sometimes it's like that, like both metals or something like that. After the reaction takes place, A is now bonded to X, so it's part of the compound, and B, which was part of the compound before, is now by itself. These are easy to spot because you have one element and one compound on each side. Here's an example of a single replacement reaction where copper reacts with silver nitrate to produce copper nitrate and silver. And this will be visible as we watch an example of this because the silver nitrate is aqueous, dissolved in water, so we won't see it. The copper will be solid. But after the reaction's done, the copper solution is now what's dissolved in water, and silver will be solid. As we watch the reaction take place, watch for the development of solid copper. It'll look kind of fuzzy and silvery, and the development of copper ions in aqueous solution, and that'll make the water look blue. Here's another example of a single replacement reaction. This guy's trying to light this mixture of iron 3 oxide and aluminum. It'll produce aluminum oxide, a solid, and it'll also produce liquid iron. As the reaction proceeds, you'll see that once it gets started, it's a pretty violent reaction, and it happens pretty rapidly. When you look at it close up, you can see a smoldering pile there, but somewhere in there is some liquid iron that's now solidified. The two examples that we just saw are of metals replacing other metals, and this is a common pattern in single replacement reactions. In zinc and copper chloride, zinc is by itself on the left-hand side, and copper is part of a compound. The zinc and the copper will replace each other and change positions. So the copper will be by itself after the reaction takes place, and the zinc, which makes a 2+ ion, will be with ZnCl2 after the reaction. Here's another example: iron and gold nitrate. Iron and gold are both metals, and the two metals will replace each other. So the gold will be by itself, and the iron will become part of nitrate, probably in FeNO3. Another pattern that we see in single replacement reactions is that nonmetals can replace other nonmetals. So here we see a nonmetal as the lone element, fluorine, and here's another nonmetal that's part of a compound, iodine. So the fluorine will replace the iodine in this single replacement reaction. This screws a lot of people up. They have a hard time doing this kind of a reaction for some reason, and they want to put the two nonmetals together. That's not what's going to happen. They're going to replace each other. So fluorine was by itself on the left. Iodine will be by itself on the right. It's diatomic, so we put a 2 there. And copper was with fluorine, and copper was with iodine on the left, so we'll put copper with fluorine on the right, and it's copper 2, so CuF2. Another common pattern is that hydrogen can replace metals if the metal is in a metal oxide, and the products are going to be water and then the metal by itself. So here's an example of a metal oxide. Iron is the metal, and it's together with oxygen in the compound. That's a metal oxide. When hydrogen reacts with it, the hydrogen replaces the metal. So hydrogen is now bonded to oxygen. That bonding produces water. And then the iron is what's by itself. This is actually a way to purify metals. This is a more common way of purifying iron. Carbon can replace metals in metal oxides and give carbon dioxide in the pure metal. So here's iron oxide and carbon. The carbon and the iron are going to switch with each other. The iron will be by itself, and then the carbon will create carbon dioxide by reacting with the oxygen. This is one of the ways that iron is produced commercially. A lot of carbon, charcoal, is put together with iron oxide that comes from ores, and at very high temperatures, this replacement reaction takes place. A lot of metals, not all of them, will replace hydrogen from an acid to give hydrogen gas. So here's an example of an acid, hydrochloric acid, HCl. That hydrogen that's part of the acid will switch with many metals, not all metals, but a lot of them. So zinc would now go with chlorine to make zinc chloride, and then hydrogen gas would be free. The metals that won't do this are actually expensive metals. This is a property of cheap metals to do this reaction. Things like gold or silver, platinum, we value those metals particularly because they don't do these kinds of reactions and they're more stable. So what are acids? Acids are molecular compounds that can release hydrogen ions when they're a part of a reaction. So an example would be HCl that we just saw. This can release H plus ions and Cl minus ions if you put it in water, or as part of other kinds of reactions. This is another famous acid, H2SO4 is sulfuric acid, and this can give up 2 H pluses and a sulfate ion. H3PO4 can give up to 3 H pluses away, plus the phosphate ion, which is PO4 3-. Here are 3 acids worth keeping written down someplace, like in your notes, because you'll have to refer to them from time to time. These are probably the most famous 3 acids that there are. Hydrochloric acid, HCl, has a lot of applications, not the least of which is dissolving your food, because your body produces this and puts it in your stomach. Sulfuric acid is battery acid, and it is the most common commercially produced chemical substance in the world. It's used for lots and lots of industrial processes. And nitric acid, HNO3, is also a very powerful acid that has the ability to dissolve even things that don't normally dissolve in acid. So here's a metal with an acid. This is a cheap metal, iron, and it's going to replace the H in HBr, which is hydrobromic acid. So we'll get H2, and then we'll get iron together with bromine, probably FeBr2. Okay, based on what you've learned about single replacement reactions, try this. Predict the products of this reaction. Stop the video and give it a shot, and I'll bring you back an answer, and you can see if you got it right. Well, this is a metal replaced metal example. Zinc is a metal, so I look in the compound and I find the other metal, which is platinum. So zinc and platinum are going to switch places with each other. That means platinum will be by itself, and zinc will be combined with nitrate. Zinc makes a 2+ ion, so the formula is ZnNO3 2. Stop the video and try this one. See if you can get this right. Well, here the lone element is a nonmetal, so I look in my compound and I find another nonmetal to replace it, and the two are going to switch. So on the right-hand side of the arrow, iodine is now by itself. It's diatomic, so we write I2. And potassium goes together with chlorine. Potassium is 1+, chlorine is 1-, so our formula is just KCl. This isn't balanced. If we wanted to balance it, we'd have to put a 2 here to balance our chlorines. Then that would require a 2 here to balance the potassium, and that would also automatically balance the iodine. Try this one, and balance it when you're done. Well, this is a metal oxide, and here's hydrogen. Remember, hydrogen can replace metals in metal oxides. The products are going to be water, H2O, and the pure metal, which is just Cu. This is already balanced as it is. Try this one. Well, this is another metal oxide, iron 2 oxide. Carbon can replace metals in metal oxides. So the metal is going to be by itself, just pure iron. And when this reaction happens, carbon dioxide is the other product. Let's balance it. Everything is balanced right now except for oxygen. I need to put a 2 in front of FeO to balance the O's, and then a 2 in front of iron to balance the iron. One more. This is an acid, and here's a cheap metal, magnesium. Magnesium is going to replace the hydrogen in the acid. So hydrogen will now be by itself, and magnesium will go together with the chlorine. Magnesium's 2 plus because it's column 2. Chlorine's 1 minus. So MgCl2 is our compound that we have when we're done. Now a double replacement reaction is like two single replacement reactions happening at the same time. These are actually easier to predict for most students than single replacement reactions are. So here we have two components that replace each other from two different compounds. The generic equation for a reaction like this would be something like this: AX plus BY, and then two things switch with each other. So B is together with Y on the left-hand side of the arrow. On the right-hand side of the arrow, B is going to be together with X. A is together with X on the left-hand side. On the right-hand side, A will be together with Y. You can spot these because they have two compounds on each side. A very common pattern in double replacement reactions is cations and anions switch partners. And you can just take the inside two ions and put them together, and that'll make one of your products. And the outside two ions go together to make the other one of your products. So in this case, we have lead-2 nitrate. So the lead-2, Pb2+, will go together with iodine. Put the outside two together. When we switch, charge swap, it's Pbi2. That's one of our products. And then we look at the inside two species and put those together, and that makes our other product. Potassium is 1+, and if you look up nitrate, NO3 1-, on the polyatomic ion sheet, you see that we have a 1-to-1 match there, and so it's just KNO3. If we wanted to balance this, we'd have to put a 2 in front of the Ki, and then a 2 in front of the potassium nitrate. Another double replacement pattern is an acid and a base create water in an ionic compound. Here's an example of a reaction like that. And again, this is the insides and outsides thing. The H goes together with the OH, and that makes HOH, which is water, or H2O. And then the inside two things go together. That's, in this case, the sodium and the chlorine, and you get what's called a salt, another ionic compound, NaCl. Here's another example. You might be asking, what is a base? Well, a base is a substance that releases hydroxide ion, has hydroxide ion in it. So just like we can spot acids by the fact that they have H's in front, we can spot bases by the fact that they have OH minuses as their anion. There are other kinds of bases, just like there are other kinds of acids, but we're not going to get into those in this class. If you see OH minus as the anion, that's a base. So let's do this example. I'll put the insides and outsides together. The insides go together, the H and the OH, that makes water, HOH. And then the outside two, strontium together with nitrate ion. Strontium's 2+, nitrate is NO3 1-. So I'm going to put parentheses around my nitrate and put a 2 down there, and that's my formula. If I wanted to balance this, I'd have to put a 2 in front of the nitric acid, the HNO3, and a 2 in front of water to balance the H's, and that automatically balances the OH's. You try this one. Well, this is an acid base. Base has hydroxide. Acid starts with H. I put the insides and outsides together again. So H with OH makes water, or HOH. And the magnesium goes together with the chlorine, inside to inside. So magnesium's 2+ because it's column 2. Chlorine's 1- because it's column 7. MgCl2 after I do my charge swap. Try this one. This is an acid and base. I've got just two ionic compounds. I'll take outsides and put them together. So sodium goes together with nitrate, and insides and put them together. So silver goes together with chloride. Silver's 1+, chlorine's 1-, so AgCl is my formula. And sodium's 1+, and nitrate's 1-, so NaNO3 is my other product. Our last class of reactions are called combustion reactions. A combustion is a reaction in which a substance burns in the presence of oxygen. The generic equation for the kind of combustions we're going to see in this class will be C something, H something. And you can put anything in for those question marks, and this reaction will be the same. Oxygen is the other reactant, because that's what's in air that burns. And the products are always consistently going to be the same, CO2 and H2O, as long as there's enough oxygen to go around and make this reaction happen. So here's an example problem. C6H14 plus oxygen. My products I know are going to be CO2 and H2O. Now here's the strategy for balancing these things. Balance carbon and hydrogen first, because oxygen is in 3 out of the 4 species in this whole equation, and so it's going to be the hardest one to balance. I start out with carbon. There's 6 carbons on the left, so I need a 6 here to balance carbon on the right. There are 14 H's on the left, so if I put a 7 in front of water, I get my 14 H's. Now, I'll add up all the oxygens on the right-hand side and see what I've got. 6 times 2 is 12, plus 7 is 19. About half the time when you balance these things, you're going to run into this dilemma. 19 is odd, but oxygen only comes in even numbers. So, as soon as you recognize that's happening, cross out the coefficients that you just put in there, and double the hydrocarbon that's burning here. Now rebalance. 2 times 6 is 12, so I'll put a 12 in front of carbon dioxide. 2 times 14, well, I'll put a 14 in front of the water, so I have 14 times 2, and now my hydrogen is taken care of. Now, when I redo my oxygen count, I have 12 times 2, which is 24. 24 and 14 is 38. Half of 38 is 19, so I'll put a 19 in front of oxygen, and that will finish balancing this. Well, now you know 5 kinds of reactions, and when you recognize these patterns, you should be able to make predictions about what products will be formed.